generation. Parity.
Oh, the parity generation. Yeah, in other words, the serial Xor device, right? Serial Xor device. Okay. So serial Xor device is supposed to do the following. It's a black box, right? And you are getting ones and zeros, right? And this is serial XOR or XOring. So what does that mean? That means every bit is processed in each clock cycle. Okay, so there's a clock cycle going up and down, okay, like that. Okay, forgive my drawings because I'm not really drawing it to scale. All right? So every single period here is one operation, right, in here. And in every single one of these periods, you XOR the incoming bits to what? To your state. Okay, so your state is going to keep all the result of all the bits that this device has seen already and the XOR of all of these bits. Okay? In other words, let's suppose that serial XORing device starts at 0, state 0, and the first bit comes in the first clock cycle, that bit is XORed with that state value, 0, that would create your new state, which is 1 now, right? Because 1 XOR 0 gives you 1. Okay, so that's your next state. So let me just draw it in time so you'll understand what's happening. So let's just start, this is your time equals 0. Okay, there's always an initial, the initial point. Okay, this is the initialization point of the circuit. Okay, you power this on and it starts at t equals 0. And from this time onwards, from left to right, okay, you see how the state changes over time. Okay, so therefore, in this particular period of time, okay, your state here, serial XOR device, is 0. That's what we assumed. Okay, if not, this is not given to you, there is no way of knowing it. I have to tell you what the initial state is, otherwise you will not know that. You will not know that. Okay? Okay, you could be asking me, for example, if I go to Selanik Church, say in Karaköy, and get one of those, D-latch or D flip-flop, how am I going to know the initial state, to begin with? Well, you'll assume it to be 0. Okay, that's straightforward now. Okay, most of the time, there is other extra inputs like reset and set. You can use them to initialize the sequential circuit to 0. Okay, but that's just what traditionally people do. They usually assume the initial state to be 0. So that's what I'm going to do here, and I assume it to be 0. Now the next one comes in at this particular period, so that's why I'm going to just use another color to show you. This is where you get the 1, that 1, and that 0 comes in here because time now flows from left to right. This is time. Okay? This is time from left to right. That's why I assume this is 1 because that's my first bit. 0 is my next bit. And then I have got another 0 because that's my next bit, right? Etc., etc. So what is this circuit supposed to do? It's going to take the 0, this is the state. State meaning that the flip-flop state, okay? That's what flip-flop stores. Flip-flop is capable of storing only 1 bit, right? Remember? It only holds 1 bit, okay? So it holds that 0, and then at the particular period, input is 1. What this device is doing, it gets that 1 and that gets 0, and then these two get XORed together. So you get a 1, right? That is your output, but also is your state. Is your new state. Okay? So that means your new state now becomes 1. Okay? And that new state is also the output. Do you remember what type of machine is that? Is this Mealy or Moore?
Mealy.
Is it Mealy or Moore? In other words, the state becomes your output. It's Moore, right? State becomes your output. You don't need to, process that information with extra gates anymore because that's your state as well as your output. In other words, the XORing output, right? So this is your new state and your output. That means it makes it Moore machine. And now the next thing you do in the next clock cycle is take the next input and then XOR it with your current state, which is 1, and you get a 1 now. That means your next state is also 1, and output is also 1. Okay? And similarly, you get 0, and then you get 1. Output again is 1, and the state is also 1. And if you keep doing this, that's the next one here. Okay, I use different colors, by the way, in a random fashion. So please accept my apologies for that. Okay, so now you got 1 and 1. If you XOR them, you get 0. That's your next state as well as your output. So this is your output actually. So what goes in here is 1 0 0 1 0, and in the corresponding bit positions in the output is 0 1 1 1 0, etc. etc. Okay, that is the serial XORing device, and I want you to design this using a T flip-flop. It's pretty easy, by the way. Okay, it's very very easy. So just think about how T flip-flop works. Okay, the functional. Just look at the table. The state table, you will figure it out. It's quite simple because from a functionality perspective, it's exactly what the T flip-flop is doing, in fact. Okay? The toggling corresponds to, in fact, XORing. XORing, you know, from logical, mathematical sense. Okay? I'm not going to, of course, go ahead and draw the circuit for you because it's your responsibility. So I'll stop here. I just wanted to, you know, convey what the serial XOR device is supposed to do. Okay, I want you to understand it functionally, what this black box is supposed to do. Go ahead.
How do we give the circuit, for example, 4-bit input?
So you give the bits in every clock cycle. You provide a single bit. In other words, if I was to draw this, I didn't draw it. I just wrote this as a logical value. But it's not, of course, how the circuits work. You have to provide them logical values. In other words, logical levels, like voltage levels, right? So if I actually have to draw the real waveform for you, this is going to be like 1, and then 0, and then 0, and then 1, and then 0, right? This is your voltage levels that you should provide as an input to the circuit.
Are we going to give the input depending on the clock?
This input is given to you by someone, like a user. The user can provide you any type of input he wants. Any combinations of zeros and ones are possible here. It's not dependent on the clock and not dependent on anything else. Only requirement that you impose on this input is the fact that this has to be synchronous with the clock. Okay, you see in this specific period of time, the voltage level here does not change. Okay, and for this period, it does not change, it's just 0. And then this is 0 again, and then this is synchronous, right? You don't see something like that, right? If I have to draw it with another color for you. For example, you don't see something like this, right? That's not valid because that's not synchronous. Okay, I want a synchronous signal. That's the only requirement on this input. And other than that, you don't have any other requirements.
I understand, but while we are implementing the multism, we can enter just one input. How do we...
one input, what do you mean by one input? Do you mean
for example,
like input is 1 bit?
Yes, 1 bit.
But that's true for a specific period. So when you start running the circuit, it now, you have to think about this circuit in terms of time, right? So there's going to be some clock here, right? Clock, and the clock ticks, right? There's a clock signal in the multism. You may have encountered that already. Are you using, okay. So in clock, that means this is time. So every single clock period here, you can provide a specific bit.
Is there a special component to make this?
Special component for providing input?
Providing, for example, 5-bit, 6-bit input.
I think so, yeah. I think so.
Can we use oscilloscope in here? This situation.
Oscilloscopes are usually used for analog components, right? Analog signals. There's I think, in multism, there is a timing diagram that you can use. Okay? Multism provides a time diagram. It's another special component that you can just, move it and then connect it. It's going to give you such a diagram, right? So that's, I think, much more appropriate for digital signals. Oscilloscopes are usually used more often with analog signals. Okay. So for your particular question, just ask that question like, how do you provide input, different bits in different periods in multisim?
Yes.
Direct that question to assistants. Okay, they're more knowledgeable about the software. Okay, there has to be a way because I've used the same software 10 years ago, and I know that there was a component for that particular purpose. So there must be somewhere.
Yes.
Since I don't use the software these days, I don't remember, so I don't have a direct answer to that question. Okay, please inquire this to our assistants. They will be more than happy to help you. Okay? All right. Okay, so this is serial Xoring device, and I just wanted to make note of this. So, so far we talked about sequential circuits, right? Sequential circuit design, and more importantly, we focused on drawing state diagrams, right? The state diagrams we had 3 different groups of sequential circuits. The first one was a sequence detection, right? A binary sequence detection problem, and we drawn actually a state diagram. Since I'm kind of feeling a little bit unconfident in terms of the way that I teach my classes, because now I've read 2 questions of the midterm, and what I've seen, my experience with your answers is that it's not at the level of I was expecting you to answer. So therefore, the grades are not, high at this point. The problem is that I thought, for example, I've taught and you guys learned about the Carnot maps very well. But it turns out that it's not the case. Because remember the second question, the last question of the second question, there was a Carnot map with don't cares, okay? Most of the guys couldn't, for example, group those ones and don't cares in an appropriate fashion, unfortunately. Which was maybe the simplest, question of the exam. However, the ratio of having that question answered correctly is quite low. That was one of the things that was interesting to me. So that's why I'm going to also go through here another question maybe, okay? With all these, practice making those practices, I believe in the next exam we have a better achievement rate of these standard questions. Okay, these questions are quite standard, by the way. So for example, in question 2, we have an XNOR gate, not an XOR gate. Most of the guys have focused, assumed it to be XOR, but it was an XNOR gate. There was a NOT here, and an AND gate. Okay, and then a CNOT gate, right? Which I provided the truth table for this, okay? And I actually named them, right? So this is XI, YI, and this was GI, TI, as I remember, okay? And I asked whether this circuit is reversible or not. Okay, so this is AI, BI. Okay. This apparently is a reversible gate, of course. Okay, because if you look at the truth table, and as I said it, I believe I did it like repeatedly. Okay, if you are able to figure out the input by just looking at the output, then it's a reversible circuit. Okay, that's the definition of being reversibility. Okay, being reversible. So there's an XI, YI, and GI, TI, 0, 0, 0, 1, 1, 0, 1, 1. And what are the GI and TI? Well, if you have XI 0, so it's just a copy of the input, but if XI is 1, then it toggles that, because it's an XOR gate. Okay, it's a controlled XOR, actually. So what that means is that 1, 0 now maps to 1, 1, and 1, 1 maps to 1, 0. That's the only difference. So if you look at this input-output relationship, if I give you output, these are outputs, by the way, right? Outputs, this is input. And remember the definition of being reversible. If you look at the output and you can uniquely determine the input, then it's reversible. So if you look at the output, if I give you 0, 0 as an output, can you uniquely determine the input to be 0, 0? Yes, because there is no other 0, 0 in this table as an output. Also 0, 1 is the only 0, 1 in the output. And 1, 0 here and 1, 1 here. So you see outputs are actually unique for each unique input. So therefore, it's a reversible circuit. Okay? But you can't say the same for this circuit because there are irreversible gates such as XNOR is an irreversible gate. Right? I mean, if you do not believe me, so let us draw the truth table for this particular component, okay? Which I would tend to say it's a half adder, but it's not, because this is not an XOR, this is XNOR gate, right? But it is close to an XOR. If you actually draw a NOT gate here, right here, right? An extra NOT gate, just put this NOT gate outside of this box, then this would be an half adder. And we know that half adder is not a reversible gate. To prove it, you can use a truth table. That means AI, BI. Let's suppose that XI is defined to be here, which I'm going to change it later on, by the way. This is just for any practical cases. I want to make you guys, remember the half adder. 0, 0, 0, 1, 1, 0, 1, 1. So what is XI, the XOR gate? It's going to XOR these 0, 1, 1, 0. What's YI? AND gate 0, 0, 0, 1. Okay. By looking at the output, this is output, right? By looking at the output, can I uniquely determine the inputs? No. Why? Because I have got two outputs here, 1, 0, 1, 0. That corresponds to the 0, 1 and 1, 0, two different inputs. That is a violation to the definition of reversibility. Okay? So that apparently is not a reversible gate or reversible component or reversible circuit. Okay? So therefore, this is not reversible. This is reversible. This is reversible also. NOT gate is reversible. Okay? So for this circuit from end to end to be reversible, all of them has to be reversible. Otherwise, you will just stop with this non-reversibility, and therefore, the circuit is not reversible. Okay? Okay, that's one of the things that you guys had, mistake, because you couldn't, handle this NOT gate very well. And suppose that GI was 0, 0, 1, 0, and TI was, I don't even remember it, but I'm going to just assume this to be 1, 0, 1, 1, 0, 1, let's say. Okay? So I'm going to just assume that this is G0, G1, G2, G3. This is T0, T1, T2, T3. Right? These are like least significant bit position to most significant bit position. So this circuit actually works on all of these bits, okay, separately. However, there's a connection between them. What is that connection? The connection is, if you got G0 and T0, so if you like to add two numbers, like A3, A2, A1, A0, B0, B1, B2, B3, so that's what you want to handle, right? This is the main objective of the question. The question asks, what's the sum of A and B? So what you need is A XOR B A XOR B0, right? A0 XOR B0. So that's your first sum, S0. But that is not available directly. What you have to do, you have to figure this out from this circuit. Unfortunately, you cannot find A0 and B0. Why? Because it's not reversible. Therefore, A0 and B0 cannot be determined by just looking at the output. But you don't need to determine A0 and B0 in order to calculate this output, because all you need is the XOR of A0 and B0, which is this particular point, right? But from that point onwards, from left to right, it's reversible. So therefore, you can actually handle this. What does that mean? That means if G0 is 0, if T0 is 1, then you reverse that. What does that mean? You don't need to memorize anything, by the way. You go to this truth table, which I've given to you. That means 0, 1, right? So I have got 0, 1 here. So what's the corresponding input? 0, 1. So it doesn't really change anything. This is 0, this is 1. Okay. And there's a NOT gate. So that means this is 1. And this is 1. Okay, good. I figured that the XOR output here, S0, is actually 1. Okay? I just, walked backwards using this reversibility, idea of reversibility. So this is the first thing you do, right? When you do this addition operation in binary domain. The next thing you have to think about is the carry information. So what is that carry information? Is it available to me? In other words, A0 and B0? Well, yes, it is available. It's right here. You already figured that out. So that means the carry information is 1. Good. Okay, that's good. I actually figured it out. Okay, next thing I have to figure out is A1 XOR B1, right? Because that's what I need to compute the next sum. Because this next sum, I know from full adder. Do you remember the full adder? This sum actually is the XOR of A1, B1, and the carry. Right? And the carry. So therefore, I have got A1. What is A1? I have to go backwards again, right? Which means, what is G1? 1. What is T1? 0. Okay. 1, 0 is right here. I have 1, 1 and Xi and Yi. So this is 1, 1. 1. But this is a NOT gate that makes it 0 here. This 1, this 1. So I have got now the XOR of A1 and B1 is 0. But I also have to XOR that with my carry that comes from the previous stage. Right? So that means 0. And XOR with 1 gives you another 1 here. So that is S1. That is 1. Okay? And you have to calculate the next carry. Right? The next carry. So the XOR of these 2 bits is 0. Okay? This could be 0, 0 or 1, 1, right? So there are actually 2 different cases. So which one is it? Well, you have to take a look at the carry information that's generated in the next propagation level, like in the second level. So that is 1. That means these are 1, 1 actually. Okay? We cannot determine the entire A, unfortunately, but some bits can be determined. Like in this case, this is 1, 1, in fact. So this is 1, 1 and the carry 1. That means sum is 1 and carry is 1, right? So that carry is also 1. Okay? So you actually keep doing this to get the final answer. So all you have to do, 2 things. Remember the full adder, how the full and half adders work, and look up the tables. Okay? The tables are given to you. Okay? So there are multiple components here that you are expected to master, okay, in order to solve this question. Otherwise, I would have given to you 2 4-bit binary numbers and I expected to solve it. Well, that's kind of standard copy-paste. That's not going to teach you anything. And that's why I wanted to ask a question like this. All right? Because you'd use actually like a lot of stuff here in order to answer this question right. Okay, not just the full adder. Okay, you learn about reversibility here. Okay, you learn about how to read off the values from a truth table like that and going backwards, right? Anyway, okay, so if you don't have any questions, so I want to also, before I start the new chapter, which is registers and counters, so let me just keep this. Let me move on to the next board. So I want to actually go through another sequence detection, okay, for you. A sequence detector such as 1, 0, 1, 1, and 1. 5-bit sequence detection. Okay? And I want you to draw the finite state machine representation of the circuit which we are about to draw, okay, together. Okay, I want to make sure that all this participation should worth a value. You came here, you reserved your time, you didn't go and play a game, right, or surf on the web. You come and over here and spend your time to learn this stuff. So I want to make sure that everybody in the room is able to draw the state diagram of this sequence detector, okay? Which I assure you, you will see a question about sequence detection in the next exam. So if you're able to draw the finite state machine representation of this sequence detector right now, you will get that answer, that question right in the exam, okay? I assure you that. Okay, so do you want to start doing it? I'll give you a couple of minutes. You start, you basically attempt yourself first, and then, we'll go walk through it together. Okay, so we'd like to draw the state diagram of this sequence detector, right? Detector. Okay. So how many states do you propose? 5. Okay. First, second, third, fourth, fifth. If we need more, I'm going to add them later on, maybe at the bottom of the board, right here. Space. Okay, so the first thing first, we have this detector, and as I said, one design approach to such a problem is to use the forward direction to encode this sequence. What does that mean? That means you can just make those transitions as you see these bits in the sequence that you would like to detect. For instance, 1 is going to cause you to move from one state, this state, to this state, okay, and output would be 0. Because that means you basically started counting those bits or having them in your memory so that you can compare whether this sequence is detected or not, right? Or accumulated or not in a given input bit stream. So it's 1, output is 0. You got 0, so you expect 0 and output 0. And then you have got another 1, and output is still 0 because you collected 1, 0, 1. Okay? And we got another 1 here, and output is 0. Now there's one more option to complete the sequence, which is to expect another 1 in the inputs. That's going to put you, so let me just name these, A, B, C, D, E. So I'm going to call or refer to these states with these letters. So I have E now. I have to move from E to some other state. Which one is that?
B.
B. Everybody agrees with that?
Yes.
And why is that? Why do I not go into the initial state? Why am I not arriving arriving this state as my destination?
Because we already have 1.
Yeah, we already have 1 in the front, so this could be the first one of another valid sequence.
Yes.
Okay, think about it in terms of windows, right? So this could be the beginning of another valid sequence. So therefore, I have to move from E to B with a 1 as inputs, and output is 1, right? Okay, so that's the first thing you need to do before you complicate your finite state machine representation even more with other arrows. But that's the first path you need to draw. Okay, the first path is the valid sequence path. I call this a valid sequence path, and valid sequence path has to be drawn first before you even think about other possibilities in each one of these states. What are those possibilities? For instance, in A, you know where to go when the input is 1, but you don't know where to go if the input is 0. That is the extra detail you need to add. So I'm going to use another color. Okay? Well, I've got another mic here. Okay, so where am I going to go if I'm in A and I see a 0 in the input?
Just take
Itself. Right? Itself. So I have 0, and output is 0 because I haven't accumulated anything. Okay? And as I said before, and I repeat again, if you're designing a detector, there's only one arrow that should have an output 1. The rest of the arrows should have output 0, because that's the valid path, right? That's the circle you're completing. Okay, now let's go to B. I know what to do if the input is 0 when I'm in B, but I don't know what to do if I'm in B and the input is 1. Where should I go? Itself. Everybody can see that?
Yes.
You guys are able to see it? Why? Why am I staying in the same state in the first place?
Because we already have 1.
Yeah, we already have 1, right? So that means I have got 1. Okay, that's good. I accumulated 1 because I was expecting a 1. But then I unfortunately receive another 1. I was expecting 0, but I couldn't. I just get another 1. That means, forget about past. Let's just start counting from the beginning. That means that 1 you got here is my first 1. Okay? Because you couldn't complete the sequence. So you don't give up. What you do is that one, to assume that one to be the first one of your valid sequence. That's why this is 1 and output is 0. Okay? Okay, in C, I'm in C. I know where to go if the input is 1. Well, what am I going to do if the input is 0? Where I'm going to go to? A? You guys A? A? Everybody?
Yes.
Okay, I go to A. What is the input? Input is 0. You know, that basically means I got 1, 0. Okay, I'm actually doing right, you know, doing very well. But then I got a 0. Unfortunately, if I receive 1, 0, 0, right, that's not going to help me. Because nothing here is the prefix of my valid sequence, right? So that means I have to go back and start counting again, like from the beginning, very beginning. That's why I have 0, 0 here. Okay? All right, when I am D, I know where to go. When the input is 1, that means I have to transition, make a transition from D to E. But if I see a 0 in the input, what I'm gonna do?
Go to C.
Go to what?
C.
C. Okay, everybody says C, so I'm going to just draw it tentatively. See if that's right. Okay, input is 0 and output is 0 apparently. Is this correct? Well, let's just check. I have 1, 0, another 1, another 0, right? So I've got 1, 0, another 1, another 0. Well, if I look at this, this is what I received so far. But when I see this, I actually see that 1, 0 could be the 2 bits of the initial 2 bits of the valid sequence. That's why I go back to C, because C actually means something in physical terms. C basically means I already have seen 1 and 0. Okay? That's why I have this 1, 0 being the first 2 bits of the valid sequence I'm looking for. Okay, that's why I go back here. Okay? And finally, E. I see E, I know what to do when I see a 1 in the input. I go from E to B. That's my transition I make. If I see a 0, what am I going to do?
C again.
C again. Why? Because I have 1, 0, 1, 1, 0. But that 1, 0 could be the beginning, right? So which means I have to go back to C again. Okay, that's why I have 0 and 0, because I haven't completed the sequence yet. All right? That's our first, of course, very knowledgeable attempt, let's say, because we verified it already. But for you, in the exam, please make sure that your state diagram is right by using some random input. Okay, and make sure that the random input generates what you want. Okay, let's suppose that this is my input. Let's suppose that 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0. Okay, that's my sequence, let's say. And if you basically have this window moving from left to right, you will basically get a 1 when you hit here, right? Okay. That's a valid sequence. So therefore, if I ask such a question, you would expect a 0 for this window, and then 0 for this one, right? So that means I have another 0 here. And when I hit here, that means that's going to create a 1. And then if I move here, and then again another 0, another 0, another 0, another 0, another 0, another 0. Okay? We didn't have any other valid sequence in this bit stream. It just turned out that way. But we could. Okay, so this is, again, one of the challenging things to do, in such a problem. You have to first make sure that your finite state machine works very well with another random input sequence. Then, of course, you have to go to the state table, by assigning all the possible inputs, 1s and 0 combinations, and then maybe state reduction, maybe that precedes that. And what follows from that is going to be the Karnaugh maps, and then drove the Karnaugh maps and make all these minimizations, optimizations to come up with the Boolean expressions, in other words, state equations. And finally, from the state equations, you draw the the circuit diagram. Okay? But all along that way, you're going to be given what type of flip-flop you should use, right? You should be told, what type of flip-flop you should use. For instance, JK flip-flop. In that case, in your truth table, you have to add J and K columns, okay? I don't want to go through all this process because we already done that standard. So I actually want you to do it yourself on a piece of paper yourself with your old handwritten handwritten thing, because that's part of the learning process. Okay, so I want to now give a fresh start to registers and counters, okay? Which is, again, no different than sequential circuit design. These are just special sequential circuits, okay? They're not really very special, but since your book has given some space as a new chapter, I'm going to basically cover them. What is interesting with those types of sequential circuits is that all of the circuits we discussed so far, they're all synchronous circuits. There are asynchronous designs as well, which is not basically the majority of the circuits we've seen so far. But I'm going to touch upon some of them because they're worth mentioning. In particular, the counters are one special type of sequential circuit, okay, that can be designed asynchronously, okay, which I'll talk about it a little bit later on. So before I start counting or counting process or counters, okay, you already are familiar with the counters actually. I mean, I can draw you a counter, right off the bat by just drawing 4 states, and each one of them could represent a number, such as 0, 1, 2, 3, and you could just make this transitions, okay, to implement a counter. If you'd like to count to 9, for example, then you increase the number of states to 9. Okay? So it's pretty simple, in fact. This is an up counter because it actually raises. You see, like it goes up to 0, 1, 2, 3, so it increases, the value increases. Or you can decrease the value by going in the counterclockwise direction, right? That's going to be the down counter. Okay? So you know how to design this because if you're given the state diagram, you know how to go to state equations, state tables, the columns in your truth table, etc., and then column maps, and then the circuit itself, right? You know the process. So that's why, as I said before, it's not something new to you. But before that, I want to talk about registers because in your CPU, you will use actually registers very much. Because registers are used to store information, okay? And you already know how to store a 1 bit, right, using a flip-flop. So I'm going to put all these flip-flops right next to each other. I'm going to stack them, okay, to create registers, because registers are capable of storing more than 1 bit. You can store 50, for example, 64 bits, 128 bits, or maybe 512 bits. Okay? These are now the register sizes of the modern CPUs today that we use. Okay? For example, AMD and Intel, they use different types of registers, and some of the registers could store up to 512 bits, actually, which requires you to, of course, design your register using 512 flip-flops, because each flip-flop can store only 1 bit. Okay? So, I'm going to start with the very basic technique of shift registers first, and then I'm going to talk about, maybe first I'll start with the parallel load registers, and then I'll talk about shift registers later, okay? Why do I talk about parallel load? Because in the CPU, you will probably have something like a move operation. What is move operation? Move operation means there's a register here that stores 4 bits, let's say, okay, and that is another register, let's say register A and register B. I didn't show you right now what these registers composed of right now, okay, just bear with me, I'll go and show you the details. But this register A stores 4 bits with 4 flip-flops, let's say, and I want to transmit, or let's say copy, this information to register B, okay, using parallel wires, okay? Okay? So all it takes is just a single clock cycle to transfer all this information from here to here. In other words, a copy operation. So the single clock cycle, meaning that in the next rising edge, I'm going to have this 1010 value to be stored in the register B. It takes only one clock cycle to copy that information using parallel wires. Okay? This is called parallel load or parallel transfer. Okay? So let me show you what's inside. The inside is not very sophisticated. You got, as you can expect, 4 flip-flops. Each one stores only 1 bit. Okay? And I'm going to use, just for the purposes of being simple, D flip-flops. Okay? So these are all D flip-flops. Okay, and then I have another set of 4 flip-flops. These are the ones, these are the destination flip-flops that I am transferring my information to. Okay? And of course, these D flip-flops will be, let us just connect this Q to D. These are Ds. D, D, D. These are Q. Okay? And of course, these are all connected to the same clock cycle. It's pretty much, you know, what you've already seen, actually. Okay, here we go. All right, this is it, right? It's pretty much it, because these are the ones, the 1010 stored in those flip-flops in the next rising edge of the clock. Okay, next rising edge. What you do actually, you basically enable these flip-flops to accept inputs, right? So therefore, you accept these inputs from these flip-flops, and these are the outputs, by the way. So that means in the next clock cycle, these 1010 values will be transferred to these flip-flops directly. Okay? This is parallel because there are 4 different wires carrying independent information. Okay? The only dependence of these flip-flops is the clock. They are synchronized with the same clock information. Okay? But the problem with the D flip-flop is that if you would like to store the same value for as long as you want, there is no such a state in the D flip-flop's truth table, if you remember, right? JK and T has that, like Q value, in their truth table or state table. However, D does not have it. D can be set or reset. It can be 0 or 1. So therefore, you have to carry this output information and put it back to D, okay, if you're not loading it, right? So there has to be some load control coming in with a mux, let's say, like mux, okay? So therefore, I'm going to connect this, and the mux select would be connected to the load information. So if load is 0, I'm going to copy whatever I'm storing in the D flip-flop again back to D flip-flop. Okay? It's kind of circle. Okay, so for example, if I'm storing 0, I'm going to store 0 in the next clock cycle. Because in D flip-flop, remember, in each rising edge, D flip-flop will look at its input and store that value. There is no QT in the truth table. Remember the truth table of D flip-flop? QT plus 1? If D is 0, QT plus 1 is 0. If D is 1, QT plus 1 is 1. There is no QT in the truth table. So it cannot really store what it was storing, okay, by just playing with the input. Okay, the input is your next state or your whatever you're storing. Therefore, we need this kind of feedback. Okay, so if load is 0, you store whatever you're storing. If load is 1, then the new value can be accepted inside the flip-flop. Okay, that's why I first wrote without the muxes. Now I'm showing you why am I using muxes. Okay, and I have to of course do the same thing for others because these are all independent. So I'm going to just draw a mux here again for the same basic reason. Okay, so that's my control signal, and that is my feedback from the D flip-flop. I've got another mux here, surely. And then I have got another feedback. And then finally, I need another mux here. Oops. So I got that. This is my D. And this is my control signal. You see the control signal load actually controls this mux, this mux, this mux, this mux. They're all in parallel. So whenever your load is 0, that means you select this one, this one, this one, this one, which means all of the bits that are stored in D flip-flop will be your next state, and will be your next state and next state, and for as long as you want. But whenever you want to store something new, that is the write command that you give to the register. When load is 1, that means these new values will be now parallelly sent to these D flip-flops, and those D flip-flops now will assume them, these values, as the new state. Okay? And then you load again, turn it to 0, then you can now store the new value for as long as you want. Okay? You know, you have to have a switch for your register, right? In order to store something, you open the switch. You write something, and then you close the switch, because otherwise your data will be corrupted with something else from outside. Okay? That's why we need to use a load, such a switch, that controls when we write something. This is actually write control signal. You know, writes in your, I mean, how many of you are computer engineers or computer science students? Most of you guys are maybe, right? So in computer science or computer engineering, writes are problematic, guys. You have to be really careful about writes. Because when you write something, you may be corrupting something that you're not even aware of. But reads are kind of easy and safe. Because you can read, Pelin can read, Kerem can read, anybody can read my value at the same time without corrupting any information. And these writes could be asynchronous as well. But in the write commands, for example, think about the file systems. In file system, there's a lock mechanism. Why people introduce such a lock mechanism in the first place? Because they don't want the data to be corrupted. When you want to write something, for example, Pelin wants to write, I give the lock to her, and she locks the file, writes something, and then closes the file or give the lock back to me, so that now I'll know that somebody can now enter the file. Otherwise, Kerem can enter, Pelin can enter, I can enter, everybody can enter the file, and all these information that we're modifying the file asynchronously. So who's doing the first thing? Right? Pelin could be kind of a little distance away from the file, and I might be close. Then my commits will actually commit earlier than Pelin, but Pelin's supposed to change the file earlier than me, maybe, right? The timing, for example, is a problem. You know, in many, so that creates something called race condition, blah, 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 blah. So writes are problematic, okay, in any engineering, computer engineering application. That's why we have a control signal for writes, but we don't have, for example, for reads. Okay, reads could be anytime you can just connect anything here and then read the value, okay? If you would like to read these register values, connect external wires to these wires, okay? And then plug them out, and then you will know what those registers are storing, okay? But if you would like to write something to your register, then you have a control signal, okay? That controls everything. If you turn it on, then you can write. Turn it off. You have to turn it off. You can't keep it turned on, because otherwise these could be changed, and those changes will be reflected to your D flip-flops. These are undesired or unwanted writes, okay? That's why you need that. All right, so the design is pretty simple, as you can see. We basically parallel the transfer. It's pretty fast, by the way. It just takes only 1 clock cycle to transfer information, okay? And in your CPU, move operation will only take 1 clock cycle, right? But not all operations will take only 1 clock cycle, right? Add operation, subtract operation, and multiplication. Think about division, okay? Very complex. It's going to take multiple clock cycles. In many modern computers, including the Intel's like i9 or maybe most advanced technology, it takes lots of cycles to do the division, particularly the floating point divisions. It takes a lot of cycles because it's a complex operation, okay? But this one is pretty simple. It takes only 1 clock cycle, okay? Did you understand the mechanism here?
Can we use master-slave approach mechanism?
Master-slave?
Yes.
For what?
For example, for...
Master-slave is actually inside this cube, right? Inside this flip-flop, right? Master-slave is used to produce a flip-flop out of 2 D latches, remember? So you can use master-slave inside your flip-flop.
Is this flip-flop?
No, this is D flip-flop. All of them are D flip-flops. You can alternatively design your circuit using T or JK flip-flop as well, right? But these are D flip-flops. In fact, if you use JK flip-flop here, right, you don't need to use this extra feedback. Correct? Because JK flip-flop has a QT in it. So you can actually, by playing with J and K, right, you can actually store the information. All right? So if I were you, I would design the same circuit using JK flip-flop. Okay, that's a good challenge for you. Just give it a try. Design your registers. These are registers, by the way, 4-bit registers. So this is your first register. This is your second register. Design those registers using JK flip-flop. You know, why not? And you would probably see that you don't need that feedback. Because that feedback, it was there because of the deficiency of the D flip-flop. Deficiency being that D flip-flop does not have QT in its state table. That was the problem with D flip-flop. In JK and T, you don't have that problem. Okay? But of course, you have to be a little smart to do the JKs. You know, you have to produce the JKs such that these transfers will happen, right? Just give it a try. If you are unable to do it, maybe in the next lecture, you remind me, I'll draw it on the board. Okay, so this is your parallel load. The other one is shift registers. So the shift register is quite using the same idea actually, but the flip-flops are connected to, you know, one after another. Okay, for example, there are 4 flip-flops here, and I'm going to connect a Q to the input of the next. Okay, and this is my first register. These are again D flip-flop, by the way, as you can guess. QD, QD, QD. This is my first register. I've got another register here, correct? Let me use green. I have got 1, 2, 3, and 4 QD, QD, and QD, and I connect them as well. Okay? Now, what I would like to do, I would like to basically put this output to the input of this D. Okay? So that's how we connect them. You see, it's serial connection. It's a serial connection. It's a single wire. It goes into here. All right, and I see. Yeah, that's pretty much it actually. Yeah, that's the only connection. And of course, their clocks will be also synchronized, right? So these are clock signals. These are all connected to the same wire. Okay. Oops. Anyway, that's my clock signal. Here. That's also connected the same. That's my clock. But of course, I need a control signal, right? In order to execute the writes, I have to do a control. What is my control? Okay, I'm going to just simply control the circuit by gating the clock, which was not a good practice, by the way, because that can cause you do some asynchronous stuff in your circuit. That's not recommended. Okay, but for this particular case, I'm going to introduce the same delay for everybody, so that is okay. However, if you introduce a gate, for example, for these type of flip-flops and not for these ones, then there's going to be an asynchronicity between them, which could be detrimental. So that's why am I not recommending it. So that's why I'm going to do the following. I'm going to put an AND gate. One of them is going to be clock. The other is the load. Okay, if the clock is going to be passed here if the load signal is 1. Okay, if load is 0, then no clock signal. That means there's no operation by these two circuits. So let me just analyze what's happening with this circuit. So, as I said, unlike the parallel version, this serial version requires multiple cycles to do the copy operation, move operation. Okay, so let's just go through it. I'm going to assume the same thing. I'm going to have 1010 that is stored initially. Okay, you could actually connect these 4 to another 4 using a parallel version so that you can copy information in one clock cycle to these flip-flops directly. Okay, then you run this shift register to shift this information to these 4 flip-flops. How? Well, clock cycles. Because in each clock cycle, this 0, in the first, for example, at the end of the first clock cycle, this 0 will be transferred to here, right? Correct. However, when you do that, of course, this is going to be shifted to here, right? And this is going to be shifted here. And this is going to be shifted here. And then this is This is the first clock cycle, at the end of the first clock cycle. However, you don't want to lose your data, right? You don't want to lose your data. So therefore, you need also a feedback that goes in like this. So in this case, this 0 is going to be copied here as well as here. Okay, so that's why you have 0 in this case. This is the end of the first clock cycle. Okay, now let's move one more clock cycle. What's going to happen in one more clock cycle? In the next clock cycle, this 0 will move to here, right? Oops. 0. This 0 moves now. This 1 now moves here. This 0 now moves here. This 1 moves here, right? And this 0 moves here. How about this one also moves here, right? That is 1. Okay, now everybody has blue, right? Okay, good. That's the next phase of the clock cycles. As the clock cycle proceeds in time, this is what you get. All right, now the next clock cycle. Are you able to see? Because of this, probably you may be having problem seeing the board. Here we go. Okay, now in the next clock cycle, what happens? This 1 now moves here, right? 1. This 0 moves here. This 1 moves here. This 0 moves here. This 1 moves here. This 0 moves here. But this 0, I'm sorry, this 0. 0 moves here and here, right? So therefore, I have a 0 here too. So now everybody has a red one, right? You got 0, 1, 0, 1. You got 0, 1, 0. Okay. Now final clock cycle. I'm going to use green again. Okay, I have 0, right? This 0 now moves here. This 1 moves here. This 0 moves here. Okay? And this 1 moves here. 1. This 0 moves here. This 1 moves here. And this 0 moves here. Okay? And also this 1 not only moves here, but also moves here, right? Now everybody has green, right? 1, 0, 1, 0. And we've got 1, 0, 1, 0. Now the copy operation is finished. Because we got 1, 0, 1, 0 in the beginning. Remember that? We got 1, 0, 1, 0, the green one. Okay, now we also get 1, 0, 1, 0. Why? Because we actually circled around it. That's why we got 1, 0, 1, 0 in the first place for this particular register. But the thing that you wanted to accomplish is to copy this information using